Time and space complexities of Huffman coding. In the last lecture, we learned about Huffman coding, which is a lossless data compression technique. Here, we are going to analyze the time and space complexities of the greedy algorithm that we learned in last lecture, which is used to generate Huffman codes. So let us try to go through each of the steps and understand what are the time and space complexities of this algorithm. So first of all, what is the input that you have? Your input is set of characters and the frequencies. And what are you going to do? You are going to generate Huffman codes for each of the characters based on the frequencies, right? So let us see each of the steps that we saw in the last lecture and let us analyze time and space complexities. What is the first step? First step is to create a leaf node for each of the characters. So you are going to create leaf nodes for each of the characters. There are a total of n characters considering your input size is n. Then what is the time taken by this particular step? In order to create n different leaf nodes, you will take order of n time. So the first step has taken up order of n time. What is the next step? Once you have n different leaf nodes, you have to build a min heap, or you can say a priority queue. So building a min heap will take order of n time. So this is the build heap process. In order to build a min heap, we already discussed in the heap lectures under data structures that building a heap from scratch will take order of n time. So your first step took order of n time. Your second step also took order of n time. What is your third step? You have to iteratively perform the following. What is it? The first thing is you have to remove two of the smallest frequency nodes from this heap. So why did you generate a heap? So that you can easily pick whichever is the minimum frequency node. So how do you pick two nodes from this heap? You will first pick the smallest node, then you will reheapify, then you will pick the second smallest node. So picking the smallest node, this will take order of log n time. How will picking the smallest node take order of log n time? You have a heap. Here you already know on the top you have the smallest node. So picking doesn't take time. You can simply take it off. But once you take the root out from the heap, you have to do a reheapify, which will take order of log n time. So till this point, the first two steps took order of n time each, and then the reheapify process is taking order of log n here. So once you take the two of the smallest nodes, what is the next step? You have to combine the smallest nodes that you picked into a single node. So you are going to create a single node out of it. This will take order of one time. It is a constant time operation because you have two nodes. You are joining them and making a subtree by keeping a root to this node. And what are you going to do? You are going to add the frequencies of these to find the frequency of the new node. So this will take order of one time. It is a constant time operation. What to do after this? You have to add this back into the heap. So how do you add it back into the heap? Again, it is an order of log n time process. Why is it order of log n? You will have to again adjust the heap so that it can accommodate this new member. So in order to do that, you will take order of log n time. So once you do these steps, you have to keep repeating these steps until your heap becomes a heap with only one single element. So now think of this. If you have a heap which is of total n elements, you have n elements, you keep repeating these steps. In that case, how many steps will it take for you to make this heap only have one element? What is happening? Each time you are taking out two nodes and you are inserting back one node, which means at each step the number of nodes that you are having in this heap will decrease by 1 because you are taking out 2, you are adding back 1. Because of that, in each iteration of your loop, you will decrease the size of heap by 1. So in order to reach from n size to 1 size, you will have to run this loop order of n times, right? So order of n times, you have to perform all these steps. So the maximum step among these is order of log n time step. So totally order of n times you are doing order of log n work. So total is order of n into order of log n, which is order of n log n. So the time complexity for Huffman coding is order of n log n. One more thing, after you complete this tree, you have to traverse it and find the Huffman coding. So how do you traverse? You have to go through the tree, the Huffman coding tree that you generated. You have to assign 0 and 1 to left and right children. So how much time will this process take? See, in this process, you are simply traversing through a tree. So in order to traverse through, you can either use a depth first strategy or a breadth first strategy. Either case, you simply are traversing through all the n nodes, which should take only order of n time. So assigning the Huffman codes 0 and 1, once you already built the Huffman tree, takes only order of n time. So order of n is less than order of log n. So the dominating term is order of log n. The time complexity of Huffman algorithm is order of log n. Next question is, what is the space complexity of Huffman coding? So coming to space complexity, we only need to consider the additional space that is taken up. Whatever is already provided as the input, that is not counted. So what is the additional space you are taking up? First thing is you want to build a heap. So building a heap means first you are building n different nodes. So taking n different nodes will take order of n additional space. You are building a heap. Heap is also of size n. So it is total order of n additional space till this point. After this, when you are removing nodes, you are not taking up any additional space. So this is okay. When you are creating a new node, that is you took 2 nodes, now you are going to create a new parent and add the previous nodes as left and right child. This will take 1 additional node but nothing else. So it should be order of 1 here. And when you do it n times, it should take again order of n time, order of n space. So totally here for adding a new node, because you're doing this n times, you may take a total of order of n space. And in this step, whenever you're creating a new heap, you want to first create n different nodes. It will also take order of n space. So total space complexity, it is order of n here, order of n here as well. So total space complexity will be order of n. So total time complexity is order of n log n and space complexity is order of n.